and tags. The art of recursion in algorithm design. In the intricate world of computer science, recursive algorithms stand as both elegant solutions and potential pitfalls. They allow us to break down complex problems into simpler subproblems, mirroring our natural problem-solving approach. This guide delves deep into the realm of recursion, exploring its fundamentals, applications, and common challenges faced by developers. Whether you're a seasoned programmer or new to algorithm design, understanding recursion is essential for mastering modern software development. Fundamental concepts of recursion. At its core, recursion involves a function calling itself to solve smaller instances of the same problem. This self-referential technique requires careful implementation to avoid infinite loops and excessive memory usage. A classic example is calculating factorials. Instead of iterating from 1 to n, we define factorial n equals n asterisk factorial n1, with a base case when n equals 0 returning 1. This demonstrates how recursion transforms iterative logic into hierarchical calls. For recursion to work effectively, two critical components are necessary: base case, a condition that stops the recursion, preventing infinite execution; recursive step, the function call that reduces the problem size while maintaining the solution structure. These elements form the foundation upon which all recursive algorithms operate. Understanding their roles helps prevent common errors like stack overflows caused by missing base cases. Diving into recursive structures. Recursion naturally lends itself to data structures with nested hierarchies, such as trees and graphs. Tree traversal algorithms often use depth-first search through recursive implementations. Consider binary tree operations where each node has at most 2 children. In order traversals visit left subtree, then root, then right subtree recursively, ensuring complete coverage without iteration. Graph algorithms also benefit from recursion, especially when dealing with connected components. Depth-first search can explore paths by recursively visiting adjacent nodes until all reachable vertices are processed. However, care must be taken with graph recursion due to cycles. Properly tracking visited nodes prevents infinite recursion that could crash programs or consume excessive resources. Common applications of recursive algorithms. Sorting algorithms frequently utilize recursion. Quicksort divides arrays into partitions, recursively sorting subsets around a pivot element chosen during partitioning. Mergesort follows a similar divide-and-conquer strategy, splitting arrays until reaching single-element lists, then merging sorted halves back together through recursive combination steps. Search algorithms also employ recursion extensively. Binary search on sorted arrays works by comparing target values with midpoints and recursing on appropriate halves until finding matches or exhausting options. Fractal generation provides another interesting application area. Recursive functions create self-similar patterns at different scales, producing visually stunning mathematical art forms. Tackling challenges in recursive programming. One significant challenge is managing recursion depth limits imposed by programming languages. Python's default recursion limit, for instance, typically restricts depth to around 1,000 levels. Exceeding these limits results in recursion error exceptions rather than stack overflow issues seen in lower-level languages. These limitations necessitate alternative approaches for deeply nested computations. Optimization techniques like memoization help mitigate performance concerns. By caching previously computed results, we reduce redundant calculations in algorithms like Fibonacci sequence computation. Careful analysis of time complexity becomes crucial. While some recursive algorithms offer O log n efficiency, others may degrade to O 2 to the power of n, unless properly optimized with dynamic programming strategies. Performance considerations in recursive solutions. Evaluating space complexity reveals trade-offs inherent in recursion. Each recursive call adds a frame to the call stack, consuming memory proportional to the recursion depth. Comparing iterative and recursive versions shows distinct resource profiles. Iterative solutions generally use less memory but may require more complex loop constructs compared to clean recursive code. Some problems inherently favor one approach over the other. For example, certain combinatorial problems become unwieldy iteratively due to state management complexities. Profiling tools prove invaluable here. Monitoring CPU and memory usage under varying input sizes helps identify optimal approaches tailored to specific requirements. Debugging techniques for recursive functions. Traditional debugging methods face challenges with recursive code due to nested call frames. Using print statements might not capture the full picture across multiple layers of recursion. Logging intermediate states at various depths proves helpful. Adding timestamps or depth counters allows tracing execution flow through successive recursive calls. Visualizing recursion trees offers deeper insight. Drawing diagrams showing function calls and return values clarifies how parameters evolve through successive invocations. Specialized debuggers with call stack visualization capabilities provide powerful tools. Tools like GDB or Visual Studio Debugger show the current call chain, making it easier to track variable changes. Best practices for writing efficient recursive code always begin with well-defined base cases. Ensuring termination conditions cover all possible scenarios prevents unexpected infinite recursion. Limit recursion depth whenever feasible. When processing large datasets, consider converting recursive algorithms to iterative ones using explicit stacks or queues. Use tail recursion optimizations where supported. Some compilers automatically optimize tail recursive calls to reuse stack frames, reducing memory overhead significantly. Profile your code regularly. Measuring performance characteristics under different inputs ensures your recursive implementations remain efficient even as requirements change. Real-world examples of recursive algorithms. File system navigation provides practical examples of recursion. Operating systems use recursive directory scans to traverse folder structures containing numerous subdirectories. Data validation routines often involve recursive checks. XML parsers verify document validity by recursively validating child elements against schema definitions. Game theory simulations leverage recursion for move evaluation. Chess engines analyze game states by recursively exploring all possible moves within given depth constraints. Solving mazes illustrates spatial recursion applications. Pathfinding algorithms use recursive backtracking to explore routes until they find an exit or exhaust possibilities. Advanced topics in recursive computing. Functional programming languages embrace recursion as primary control structures. Languages like Haskell and Lisp rely heavily on recursive functions instead of traditional looping mechanisms. Continuation passing style, CPS, transforms recursive algorithms into non-blocking operations. By passing callback functions as arguments, we enable asynchronous processing in otherwise synchronous designs. Lazy evaluation optimizes recursive computations by deferring calculations until absolutely necessary. This approach conserves resources in memory-intensive applications involving large datasets. Parallelism introduces new dimensions to recursion. Dividing recursive tasks among multiple processors enhances performance for computationally intensive problems. Pitfalls to avoid in recursive programming. Oversimplifying base cases leads to subtle bugs. Missing edge conditions in termination criteria can cause unexpected behavior in seemingly simple implementations. Ignoring stack overflow risks damages program stability. Calculating recursion depth upfront helps avoid exceeding language-specific limits that would trigger fatal errors. Overlooking optimization opportunities slows performance unnecessarily. Simple memoization improvements can drastically enhance algorithm speed for many recursive problems. Confusing recursion with iteration causes unnecessary complexity. Choosing the right paradigm based on problem characteristics simplifies both coding and maintenance efforts. Comparing recursive versus iterative approaches. Readability differs significantly between approaches. Recursive code often mirrors problem descriptions more closely, enhancing maintainability despite potential performance drawbacks. Memory consumption varies inversely with approach choice. Recursive implementations tend to use more memory due to call stack storage, whereas iterative variants manage state manually. Execution speed depends on specific implementations. Well-optimized recursive code can match or exceed iterative counterparts' performance, particularly with memoization applied. Conversion between paradigms remains possible, though sometimes challenging. Many recursive algorithms have equivalent iterative formulations requiring careful transformation. Tools and resources for mastering recursion online platforms offer interactive learning experiences. Coding websites feature exercises that gradually increase difficulty, helping solidify conceptual understanding. Books dedicated to algorithms provide theoretical foundations. Classics like CLRS, Introduction to Algorithms, explain recursion principles alongside practical implementations. Code repositories host open-source projects showcasing real-world applications. Studying existing implementations helps bridge gaps between theory and practice. Community forums foster knowledge exchange. Engaging with experienced programmers addresses doubts and explores advanced topics beyond basic tutorials. Conclusion: mastering recursive algorithms unlocks powerful problem-solving capabilities in software development. Their elegance lies in transforming complex tasks into manageable subtasks through hierarchical decomposition. To excel in algorithmic thinking, practitioners should balance theoretical understanding with hands-on experimentation. Embracing recursion's strengths while mitigating its weaknesses enables creation of robust, efficient solutions.